Section 11.4, Boyle's Law. So there's a number of gas laws, and they're named for the people who discovered them. And these experiments with gases were back in, I think, like the 1700s, long time ago, well before there was electricity. And so they did all these experiments under very primitive conditions, and yet they came up with laws that we still recognize today, which is kind of cool. So we'll mention their names, but I'm not going to quiz you on their names, okay? Because what I want you to learn is how to do the problems. I'm not going to quiz you so much on chemistry history. So Boyle's law relates pressure and volume. The pressure of a gas sample depends in part on its volume. It depends on some other things as well. But what we find is if we keep the temperature of the gas and the amount of gas constant, the pressure will increase if we decrease the volume. The pressure will decrease if we increase the volume. So think back to those two jars, same amount of gas at the same temperature. The jar with, no, that's not a good analogy. Never mind. That's Avogadro's law. Never mind. Scratch that. Yes?
So I understand that water attracts each other and gas doesn't attract. Does it repel? Like if you had a jar the size of Earth, and you had just a tiny bit, it would just keep going forever?
It would just keep going. And it's not that the particles repel each other. It's just that they're so completely not interested in each other. They bounce off and they'll just keep going until they run into something.
Oh, that makes sense.
Okay, so a gas particle, so maybe you had this huge volume, like gymnasium or something, or the Metrodome or something, big volume, and you had a little tiny bit of gas that was all squished into like a little propane cylinder or something, and you let it go in there. It was complete vacuum. Those gas molecules they're moving, they're going to go in a straight line until they run into something. If they don't happen to run into another gas molecule or the side of the container, they're going to go until they hit the other side of the container. And so that's how gases spread out.
An object in motion will stay in motion?
Yeah.
Oh.
Yeah, until it runs into something.
Yeah. That makes
Yep.
sense.
So let's look at a simple hand pump. You might have one of these for pumping up the tires in your bicycle. When you lift the handle up, the upstroke, when you lift the handle up, you're increasing the volume of the cylinder. So what's inside of here is a piston, kind of like that one we looked at earlier when we talked about gases being compressible. And so we lift this up, and now the volume in here increases. There was some air in there. The volume increases, the pressure inside this now decreases. And what happens? It allows air to come in. There's a one-way valve at the bottom, which allows air to come in through this valve. And so when we raise this up, air will flow in there. Kind of like when you're sucking on a straw, it'll come in. Okay, when you push down on this, the downstroke, now you're decreasing the volume. You're squishing the gas in there together, smaller volume, same number of particles, same pressure, I'm sorry, not same pressure, the same force, but smaller volume, then the pressure increases. The pressure increases, and that air is forced out of this tube into whatever you're inflating. And so you lift it up, the air comes in the one-way valve, you press it down, it can't go out that valve, it has to go out this way, and it'll go into the bicycle tire or the ball or whatever it is that you're inflating. Does that make sense? So that's how the hand pump works. We describe these relationships between gas properties by gas laws. So actually this was the 1600s. Robert Boyle lived from 1627 to 1691. That was a long time ago. My husband had an opportunity a couple summers ago to go to England and study the history of chemistry, and he went to Oxford and Cambridge and the Royal Society. And a lot of these, like Boyle was an English guy, you can kind of guess from his name. They have some of his original equipment and some of his lab notebooks, and my husband actually got to look at them. He's a chemist, so he thinks that's cool too. But it's crazy. They still have all this stuff preserved. This is a long time ago. But he studied the relationship between pressure of a gas and volume. And so we call it Boyle's law. And Boyle's law assumes that we're keeping the temperature constant and the amount of gas constant. So we're not putting more gas in or letting gas out. We're keeping the number of particles the same, and we're also having the temperature be the same. So he found that the volume of a gas and its pressure are inversely related. So that means when one goes up, the other goes down.
How did they keep the temperature constant back hundreds of years ago if they didn't have like air conditioning or anything?
That's a good question. It's actually pretty easy. So you change the volume of the container, and initially that will cause a change in temperature. But if you wait, it goes back to room temperature. So it just involves a little more waiting. You could do it in an ice bath or a boiling water bath to control the temperature that way too. They were very creative, very creative. So, you know, he would change the volume of a container with an amount of gas in it, and then he would look at how that changed the pressure. So one way to express his law is V, which stands for volume, and this alpha symbol means proportional to 1 over the pressure. So if P gets bigger, then 1 over P is smaller, so the volume goes down. So if the pressure goes up, the volume goes down. If the volume goes up, the pressure goes down. It's an inverse relationship. And if you think about balloons, a lot of these things we can remember just by thinking about a balloon. How can you get a balloon to be smaller without letting gas out? You could compress it, right? You could put more pressure on it, squeeze it together. If you add pressure, if you increase the pressure of the gas in the balloon, it's going to make the volume be bigger. I'm sorry. Never mind. That was backwards. If you make the volume smaller, the pressure goes up. Yeah. Sorry. I get ahead of myself sometimes. And I don't know. I've got Avogadro's law stuck in my brain today. So this is the sort of thing that he did. He used these J tubes. And so you have a gas trapped in here, and you have mercury, and then the outside is open to the atmosphere. So if the pressure inside is equal to atmospheric pressure, then the levels of the mercury on each side are the same. Here, the level of the mercury here is lower than over there, which tells us that the pressure inside is greater because the pressure of this gas is pushing this column of mercury down. And you can measure the pressure by measuring the difference in the heights of the columns of mercury. So no fancy equipment, a bent piece of glass and some mercury. And they could do all kinds of cool stuff. How do you add pressure to the gas? Well, put more mercury, push the wrong thing again. Put more mercury into the tube. So the mercury is pushing down. You add mercury to this side, and the gas volume decreases. And the pressure difference is this H. We see the pressure is greater, and the volume is smaller. And you can graph these things. So here, changing the pressure and measuring the volume, and we graph this. At low pressure, we have large volume. As the pressure increases, the volume decreases. And we've got this curved relationship. Any questions? This relationship is explained by kinetic molecular theory. So here we have a piston, and we've got, this is a brass weight on top. And here we're increasing the brass weight to push down. So we're taking the volume from 1 liter to half a liter. So we're cutting the volume in half by putting more weight on this piston and causing it to go halfway down. And we can measure the pressure with a little pressure gauge. And we see that the pressure went from 1 atmosphere to 2 atmospheres. If you cut the volume in half, the pressure doubles. If you double the volume, then you cut the pressure in half. So it's this inverse relationship. A more useful way to express Boyle's law is this way. P1 V1 equals P2 V2. And we could go into the derivation of this from V is proportional to 1 over P, but I don't think anybody's that interested, so we'll skip that. So we can do some calculations, and here's a Boyle's law calculation. So here come more story problems, word problems. A cylinder equipped with a movable piston has an applied pressure of 3 atmospheres and a volume of 5 liters. What is the pressure of the cylinder if the volume is decreased to 2 liters? So the volume is going from 5 liters to 2 liters. The volume is decreasing. What do we expect the pressure to do? We expect the pressure to go up, right? But this is not so obvious as the previous illustration where we cut one in half and we doubled the other. So we need to actually do a calculation. Part of the hard part of this sort of calculation is organizing things and getting them straight, because you've got 2 pressures and 2 volumes, and it's easy to get them kind of mixed up. So the best way to do this is to make a table. We're going to have 2 sets of conditions, and we'll just call them 1 and 2. And it doesn't matter if you call one set 1 and the other person calls it 2. It's just that you get them paired up correctly. So we're going to have 2 sets of conditions. We go through the problem, and we read it, and we write down the numbers as we come across them. It has an applied pressure of 3 atmospheres. So we'll call that condition 1, 3 atmospheres. And it says that's pressure. So we're going to label this column with a P. That's pressure. 3 atmospheres and a volume of 5 liters. Those 2 go together. Do you see that? That pressure and that volume go together. So it's 3 atmospheres when the volume is 5 liters, and that's V for volume. So that's the first set of conditions. What is the pressure? That's the question mark. And if the cylinder, if the volume is decreased to 2 liters. So down here then we see that the volume is changing to 2.0 liters, and we've got 1 empty box. You should always have 1 empty box. And what we're going to do is we're going to call that P2. That's what we're trying to find. We call it P because it's the P column, and subscript 2 because it's the second set of conditions. Everybody following me on how I took those words and made a table out of it? We're going to be making a lot of tables like this. So we got to get this straight. The sooner you get it straight, the better. And so then we see that in this problem, which of course this is the first law we're talking about, so we only have the 1 equation, but later we'll have several different equations, so you have to figure out, well, which equation should I use? Look at your table. What letters are in the column headings? P and V. We need the equation that relates P and V, and so it's P1 V1 equals P2 V2. Always makes me want to say R2D2. Now we have to do a little bit of algebra. We want to get P2 by itself. We want to know P2 equals what, and because we've got numbers for the rest of them. Do not plug the numbers in and then rearrange the equation. That's a recipe for trouble. Okay? Students are like, but I like to do it that way, and so I went with that a couple of times. It's not good, so we're not going to do that. Rearrange it first. Believe me, it is easier. So if we get P2 by itself, we have to get rid of V2. So here's your algebra lesson. To get rid of that, we want to divide by V2, because anything divided by itself is 1, right? So we can get the V2s to cancel out, to poof, go away. But in order for this to stay equal, we have to do the same thing to both sides. If you have a balanced teeter-totter and you put a 5-pound bowling ball on one side, you better put a 5-pound bowling ball on the other side and keep it equal. So whatever you do to one side, you have to do to the other. So we divided by V2 over there, so we need to divide by V2 over here. Now you may want to just rewrite this so that you can see it more clearly. P2 equals P1 V1 over V2. Be very careful when you're copying these down. Okay, because we've got multiple variables. We've got P's and V's, and we've got 1s and 2s, and it's really easy, even if you have no tracking or dyslexia issues or anything, it's still easy to mix them up. So double check. Now we go over to our table, we've got everything organized, and we see, well, what's P1? Well, P1 was 3 atmospheres. So we're going to write that in here. Include the units, okay? Just believe me. P1 and V1, V1 is 5.0 liters, and that's going to be divided by V2, which is 2.0 liters. So then we get out calculators, calculator, 3 times 5, should be able to do this in my head, but I don't feel like it. So P2 equals, and how many sig figs should this have? 2, because all of our numbers had 2. So 7.5. Let's look at what happened with those units. These liters canceled out, and we've got 7.5 atmospheres. Any questions? Yes?
For P1, the pressure is less than the volume, so P2, the pressure is going to be higher than the volume? I thought they were supposed to be equal.
They're not equal. The pressure times the volume stays constant. And so sometimes the volume's higher and sometimes the pressure's higher. What we're looking at is the change in pressure from 1 to 2. The volume went from 5 to 2. So the volume decreased, then the pressure should increase. Okay? It's a good question. So you do it, you make sure your units cancel out, that's always a good sign, and then ask yourself, does the answer make sense? We predicted that the pressure would go up, and it did. So a common mistake is people get things upside down, and then you'll have your pressure going down instead of going up, and you look at that and you're like, wait a minute, that doesn't make sense. And because you wrote all your work out, you can go back and find where the little glitch was. Any other questions?
When it's P1, V1, those both equal 15, what would that be? 15 atmospheres? It wouldn't be atmospheres per liter.
It would be atmosphere liters.
15 atmosphere liters?
Yeah. Yeah. So, what was it? 3 atmospheres times 5 liters would be this 15 atmosphere liters or liter atmospheres, depending on how you felt that day. Pardon me? It would not be a slash. And so one of the things, when we say that the volume, I'll get it right, yeah. Volume is proportional to 1 over P. That means that volume times pressure equals some constant. And so the volume in the first one was 5 liters. And when we multiply that by 3 atmospheres, that's a 0. The number we come up with is 15. And then the units are like variables in algebra. If you have x times y, it's just x times y. So we just have liters times atmospheres. Liter dot atmospheres. And that looks weird, but it's okay. That's what it is. And so then in the second situation, the volume times the pressure must equal that 15 liter atmospheres. Well, the volume now was 2 liters, and the pressure is what we didn't know. And we look at that and we say, well, the P must be 7.5, because 7.5 times 2 is 15. So that's kind of a different, more math reasoning way of looking at it, but you end up with the same thing.
Divide by 2 would 7.5.
Right.
So if liters divided by atmosphere would be liters per atmosphere for atmospheric pressure per liter, what is liters times atmosphere?
Liters times atmospheres is just liter atmospheres. I know.
So, when what we're really.
There's a whole, I mean, you get into physics, there's all kinds of weird units, and they just take these units and they multiply them and they divide them and they square them and they cube them and they cancel out, and they're just like little happy.
Mathematically, it makes sense, but I'm trying to relate that back to real world and what that would mean. You know?
Well, it doesn't really mean anything. Liter atmospheres doesn't really have much meaning in terms of a quantity that you can think about.
Okay.
Yeah.
Would it be 15 liters of air at sea level? Like if you went to sea level and you just grab 15 liters of air, that's all it is, right?
Well, but it's not at,
Isn't that an
it's not at 1 atmosphere. It was 15 liters at 3 atmospheres. So if it was at 1 atmosphere, what would the volume be?
What is here?
15 liters?
Well, if it was, that's at 3 atmospheres of pressure, right? You have 15 liters.
So volume times pressure, we said equaled 15 liter atmospheres.
Okay.
So now if the pressure equals 1 atmosphere, well, 1 atmosphere times the volume must equal this 15 liter atmospheres, right?
So it's 15 liters.
So it's just 15.
15 times 1 is 15?
Yes, I misunderstood your question.
Oh,
Yes,
okay.
you're right, sorry.
So that's the quantity you said you can quantify. That's what I was saying. Like if you just went to sea level and grabbed up 15 liters
Right.
of air.
Because it doesn't matter where the pressure is, as long as you're having, depending on, just the volume is volume regardless of where it's at.
Yeah, if you change the pressure, though, the volume's going to change.
Yeah, but the pressure stays.
But here we're talking about the same sample of gas, we're not letting any out, we're not putting any in, and the temperature's the same. Because we'll find out next that if you change the temperature, things change.
Oh, yeah.
And if you change the amount of gas, things change. So we got pressure, volume, temperature, and amount of gas. So we got 4 variables. And they all change relative to each other.
Cool.
It's very cool. I think it's cool.